Hi everyone. This is another lecture for Kinesiology 376, the undergraduate biomechanics class. For this lecture, we're going to be doing an introduction into kinetics, excuse me. And the big difference from what we've done so far is we've talked about kinematics, and where we try to describe motion, but we're not talking about the reason for that motion or what caused that motion. In kinetics, we're looking at forces. Forces are what causes motion, whether an object or system or body is at rest and it begins to move, or whether it's already moving and it changes its movement, whether it speeds up, slows down, goes in a different direction, stops. That's what we talk about kinetics. We're talking about forces. So for this lecture, we are going to talk about the center of mass and center of gravity. We're going to define what mass is, what force is, weight and pressure, the moment of force, what impulse is, and distinguish again between scalar and vector quantities. Forces are vector quantities, which means they have a magnitude and direction. We're going to add another qualifier onto force as a vector in a little bit. But forces are not scalars, okay? Scalars just have a magnitude. Also, there's not really a video for this, but I've placed this link right here. I was hoping to highlight that, but this link right here is a good kind of article and discussion about the importance of understanding these forces. It talks about the training of Simone Biles. She's an Olympic gymnast, and she's basically pretty much has basically she's like a next generation gymnast. I was kind of struggling for those words there. So let's get started. So kinetics is a term used to describe the cause of movement. So once again, we're talking about forces, we're talking about power, which is the rate of work, and energy of that movement. Kinetics, a good example is when we activate the biceps and triceps when they're both activated, does the form go into flexion or extension? It would stay still because we're looking at the activation of an agonist and antagonist. If they're both activating with the same amount of force, we would say no movement. That's what we call our equilibrium. We could also determine how much force the ankle does when it absorbs this force during gait, or how much force does the ankle joint absorb during gait. And then the human body, we'll talk about how it both generates and resists force during the course of our daily activities. So, the basic concepts. Force. Force is equal to the mass of an object times its acceleration. This is actually Newton's second law of motion, and we'll talk about that later. We'll talk about that in our linear kinetics discussion. Mass is not necessarily weight. Mass we call it kilograms, but we're looking at basically the amount of space an object takes up. So when we say mass, we're not really talking about weight. Mass and weight are a bit different. Weight is actually a force. Weight would be equal to the mass of gravity of where you are. So on Earth, it's 9.8 or 9.81 meters per second squared. When you step on a scale, you're measuring your weight. So when we talk about kind of, it's a common physics teacher's joke, which gets old after a while, but, you can't ever really lose weight. You can lose mass, but you can't lose weight. The only way of actually losing weight is start chopping bits off yourself or move to a different planet with lower gravity. And we'll talk about inertia, which is simply, we'll talk about inertia, which is simply an object's resistance to a change in motion. We'll talk about pressure, the moment of force, which is force times the displacement or distance of a lever arm. Moment of force also has another name. We call it torque. if you look at your car, you have horsepower and torque of the engine. This moment of force or torque is what we consider to be our rotational force. In some of the lectures, I started talking about if we knew the lever arm and we knew how much force it was, and we did some trig, let me change the color of that. We did some trig, which we like to do in biomechanics, and we have our right triangle, and we know these angles here, and we know our opposite, our hypotenuse, and our adjacent. We kind of use trig to look at our forces. So our hypotenuse will just say force of z, our adjacent is force of x, our horizontal component, and then force of y, which is our vertical component, is actually our rotational component. Rotational component. I spelled that wrong, but what are you going to do? So, a rotational component. So when we're looking at how the moment of force, or we're trying to discover torque, we're using f of y. Okay, and we'll talk about that in a bit. But a lot of times when we look at this, we're using, sine of theta to discover what f of y is. Okay, and that's our moment of force. Our impulse is simply a change in momentum, and we'll talk about what momentum is later as well. But an impulse is a change in momentum or a change in motion, and we can calculate that as well. So mass, once again, it's a quantity of matter composing a body. It's not weight. In biomechanics, we use kilograms. This is our metric unit for this. If we're looking at imperial, we'd use slugs. We won't use slugs because we don't use imperial, we use metric. So often we'll say kilograms. Sometimes we'll say grams, and you'll be expected to convert to kilograms unless it's otherwise specified. Inertia is the resistance to a change in motion. Okay, so better way of saying it is the tendency of your body to maintain its current state of motion, whether it's motionless or moving with a constant velocity. When we say constant velocity, we're saying speed and direction. So our magnitude and direction. Okay, so inertia is a resistance to change in motion. If we're motionless, we're just standing. Okay, we need to create enough force to overcome our inertia to begin moving. If we're running, or let's say we're jumping towards something, for us to stop moving, we need to have enough force to overcome the inertia of our motion. Okay, so remember, inertia is resistance to change in motion, any motion whatsoever. So whether it's rotational motion, linear motion, we'll have a lecture on angular kinetics as well after we do linear kinetics. Once again, the difference between linear and angular motion, or linear and angular kinetics, most of the time when we look at this, the math really doesn't change that much. We're usually just swapping units. It changes a little bit, but not by much. So remember, resistance is a resistance. Inertia is a resistance to change in motion. So, for example, let's say we have a 200 kilogram weight. It tends to remain motionless. However, skater gliding on ice would continue gliding, okay, without an opposing or additional force that's needed, that's required to change that state of motion. And it has to be equal to or greater than the already present force to change that motion. Usually when we look at inertia, inertia has no units of measure. It's a ratio, so it doesn't really have units of measure. But usually when we increase mass, we increase inertia. So something that is heavier has greater inertia, where it's harder to move it or to change its state of motion than an object with less mass. When we talk about force, force can be thought of as a push or pull acting on a body, okay? And it's drawn as an arrow or vector. It's characterized by, once again, the magnitude, the direction, and then also the point of application. So let's take a look at our two ways in which force can be applied. When we look at the muscles of our bodies, or the muscles of our body pulling on our bones, we're usually looking at a pulling force, and this has our direction, okay, our magnitude due to the length of the line, and our direction is determined by the tip of the arrow, and then our point of application. Our point of application is right here, okay? So that's where we are applying this force. If we're pushing something, we still have our direction, indicated by the tip of arrow, our magnitude, indicated by the length of this arrow, and then our point of application. This person is pushing at this point. That's our point of application. Our point of application, we'll talk about it further later, but how this force is being applied is just as important as the magnitude or direction of that force. Generally, the point of application of a force dictates how a system will begin to move. So when we look at our muscles, our bicep muscles, and it's pulling on the arm, once again, if we're looking at somebody doing arm flexion, they're doing a bicep curl, this would be our vector here. So this is our magnitude, our direction, and then this is our point of application. Okay, just POA, point of application. And so then our arm is going to flex upwards like this. In a football tackle, this right here, this person's moving like this. Let's change to a different color so it's easier to see. Person is moving like this. Keep messing up my colors. Moving like this. This is our magnitude. This is our direction. And right here is our point of application. Okay? So when we look at our muscle, once again, it's shortening towards its center. It's doing a concentric contraction and pulling up on the forearm. When we look at this football tackle here, here's how they're moving. So this is our magnitude, our direction, and then our point of application right here. So a note on what we consider our ground reaction forces. This has to do with Newton's third law of motion, which we say with every action there's an equal and opposite reaction, okay? When we push off the ground, let's say we are trying to jump or we're walking or we're starting to run, we are pushing against the ground, okay? So here we are pushing against the ground, and then the ground responds by pushing back at us with the opposite direction and the same amount of magnitude, okay? That's the reason we start moving, is the ground pushes back on us. If it didn't, our foot would go straight through the ground and we travel to the center of the earth and bounce around for a bit. So it's very, very important that we look at this, that there is our ground reaction force is an equal and opposite force. So once again, the runner is pushing down and backwards against the ground. The ground pushes upward and forward. This is our reaction force. Therefore, the runner moves, it's also equal and opposite. Therefore, the runner moves forward and upwards, okay? We draw the ground reaction force rather than the force the runner creates, okay? Remember, when we're looking at a human body, especially if we're looking at they're moving, they're running, they're walking, the ground reaction force becomes very important because that's essentially what is causing that motion. It's that reaction force. So, some common forces acting on the human body. We have our gravitational force. This is kind of our weight. Remember, weight equals mass times gravity. Gravity, as long as we're on Earth, is usually 9.81 or 9.8 meters per second squared. We have our muscle forces. So we do have, our translational force, or F of x, which we often use cosine for. But when we're looking at kind of a rotational motion, we're looking at kind of the end outcome, the more general outcome of a muscle pulling on a bone. We're often talking about the horizontal or the vertical component, or F of y, which we often use sine for. Then we have friction, which we'll talk about in our linear kinetics discussion. Friction is simply, it's a force that is applied opposite to the direction of motion. It's a resistance force. And then we have air resistance. If you're wearing very baggy clothing on a windy day, the resistance from just the wind itself is going to push back on you. Okay? Usually when we calculate air resistance, we're looking at the force and area in which it's applied. And then if we wanted to go a little bit deeper, we could talk about if motion is occurring in liquid, like you're swimming in a pool. We can look at the buoyant force. Our buoyant force is often substituted for our ground reaction force. It's usually equal and opposite. We can talk about water resistance as well. And usually when we're talking about forces, it's always force equals mass times acceleration. Okay? Newton's second law says the force of a moving object is proportional to its mass and its state of acceleration. In metric, we use Newton. Once again, he wrote the laws of motion, so we're going to give him his due justice and say, well, we'll measure force in newtons. In biomechanics, we usually use just newtons. If we're looking at more mechanical systems or larger systems, we may use kilonewtons, meganewtons, things like that. Okay, imperial, we're using the pound. Okay, so if you're looking at calculating in imperial, you're trying to figure out force. Often we use pounds. So we're not really looking at a force equals mass times acceleration when you're measuring mass in pounds. Remember, you're in the imperial, you're measuring mass in slugs. Okay? In kind of kinetics and physics in general, if we're looking at imperial units, forces are measured in pounds. But we use metric, so we're using the Newton. Also, when we look at kinetics, we often draw free body diagrams where you're not really judged on your artistic ability, as you can see from my terrible writing and everything like that, where we're just drawing the forces on an object. We're using arrows and lines. This is the first step taken when we're analyzing the effects of forces on a system. A free body is any object, body, or body part that is being focused upon for analysis. Okay? We use these free body diagrams to basically try to figure out what the net force on an object is. This net force is the overall effect of many forces acting on a system. Our body is constantly subjected to a multitude of forces, from gravity, our ground reaction force, the forces of the rotational force of our muscles. Once again, if you're standing outside on a windy day, air resistance. So we like to look at the net force. This net force is the sum of all the vectors of all the forces that we're concerned with, and this usually determines the direction of movement. So some of our free body diagrams that we want to determine the bicep force to hold the forearm horizontally. So we have this here, but one way we might do it is, once again, this is our humerus, forearm, and then we have the weight of our forearm. I'll just put forearm. We have, which is determined by gravity, if we're holding a weight in our hand, that's the force of the weight. And then we have our muscle force. If we're looking at the bicep, it's going to go like this. It's going to insert into our form. And once again, we determined, we created another right triangle. So we have our F of y, our rotational force, our F of x, which we sometimes call our translational force. It can be a stabilizing force when we're looking at our stabilizers and neutralizers. Our stabilizers, if we're looking at the biceps once again, they're pulling like this, okay? So we have our F of y is going up, our F of x is going towards the elbow joint. This is nice because it helps stabilize that joint. It brings it to what we consider to be a closed back position, so it makes it more stable. So we have a very stable platform in which to pull from. And we'll consider this hypotenuse, we'll just call it F of R, or the resultant force. This is basically the sum of the force of the bicep. So then once again, we calculate F of y, and it's usually going to be, most always, is the sine of theta. Okay, and we'll talk about that later. We use the sine of theta equals our F of y, and usually our cosine of theta is our F of x. Okay, we won't talk about the resultant force really, because that's where we'd start using our Pythagorean theorem, that a squared plus b squared equals c squared. We don't really, if you're thinking of using the tangent to calculate F of r, technically you can, but it's more proper and it's a lot more accurate to simply use the Pythagorean theorem for this. So let's talk about our center of mass. This is the point around which a body's mass is equally balanced in all directions. It gives an index of total body motion, okay? So when we're looking at body motion, we determine that body's motion from the center of mass. We're saying we're moving that center of mass. It determines the manner in which the body responds to forces, our net force, okay? And it can be altered by moving our limbs. We'll look at an example in a little bit, but if we throw all our limbs towards the right, we may shift our center of mass towards the right, okay? And we often mark the center of mass with the center of mass symbol. It's this little one right here, okay? And it's at the center of where most of our mass is. So if we're looking at a human, it's often in the trunk, because that's where we see most of our mass is kind of placed. It's usually around our trunk. So let's look at some other kind of objects. So we have just a general ball or circle. Our center of mass is going to be straight in the middle of that. This becomes important too, especially when we start looking at angular kinetics, because when we start measuring the lever arm, or we're trying to figure out the moment of inertia, we need to know the length of the lever arm. And we'll talk about that in a bit. It's usually a symbol like this, distance of the lever arm. And it's determined by the radius from the center of mass to the outside. So this is our radius right here. We often determine that when we were looking at kinematics, angular kinematics, and we were trying to determine the linear velocity by knowing the angular velocity, and we multiplied it by r, by r. This is r right here. This is our rotation. This is the radius of rotation. If we're looking at just a cylinder, or like maybe a 2x4 or a rectangle, it's going to be smack dab in the middle of that. If we're looking at another object that has a little bit more vertical mass to it, it's still going to be in the center. This could be an O-ring or a tire. It's got a hollow part, but once again, all the mass is congregating towards the center. If we're looking at a cylinder, it's going to be in the middle. This is our little trapezoid right here. It's going to be a little bit lower just because this is where we see more of the mass. Instead of it being up here in the center, it's going to be a little bit lower because there's more mass on the bottom side. And if we're looking at a baseball bat, assuming that it's a properly balanced baseball bat, they haven't been cheating and tried to cork the bat or anything like that, it's going to be around the center, away from the handle. Because once again, this is where most of our mass is in a baseball bat. So it's going to be closer towards the center of the actual bat part instead of the handle right here. So this would be this is, I guess we could call it the bat part of a baseball bat. So when you have more than one segment, we draw the center of mass for each segment. And then we draw a line between the segments' centers of masses. Okay? This is how we develop our free body diagram. If the segments are equal weight, the center of mass will be located at the midpoint of the line. If a segment is heavier, the center of mass will be closer to the heavier segments. When you're looking at the baseball bat, the handle of a baseball bat is going to be lighter than the bat part of the baseball bat. I don't know the actual term between the handle and the rest of the baseball bat, so let's call it the bat part of the baseball bat. But so when we looked at our baseball bat, the center of mass was more distal from the handle, okay? And we assume that thickness and length of the segments in the examples indicate the relative heaviness of the segments. So let's take another look at some other things here. So we have just this almost looks like a protractor. So we look, these right here are fairly equal. So we'll say the center of mass is going to be pretty equidistant from both ends. It's going to be straight in the middle. This here, we see that, this looks a little bit lighter than this side. So we may have a center of mass that's closer towards the heavier side. And here, we've changed this just a bit. We've basically brought this side closer to this side. So the center of mass may be right about here. Okay? And then we'll start looking at this again. This we can almost assume is a body. I don't know how that got there. But let's see if we can get rid of it. We cannot get rid of it like that. Or like that. Oh, we did. Okay. Good. So if a person's standing, the center of mass is going to be right about here. When they start leaning forward, it's going to go forward like this. So that's where we start. Our center of mass may be closer, maybe more anterior. Then we look at, well, we've added a head. So the center of mass is going to be right there. We've added arms, so it's going to be right there. That got deleted. Stop deleting that. Be right here. Okay, and then we have a center of mass here and a center of mass here. So that's where we start drawing lines to see where they all intersect. So our center of mass might start moving more anteriorly like this. That's where we start looking at possibly the strength of our posterior muscles to make sure that we are balanced. So if we're looking at a human here, let's say that they're just kind of standing normally. Their center of mass, for most humans, we're looking at kind of the belly button area right here. That didn't look too good, but right about here instead. That's kind of their center of mass of their body. I'm going to redraw it just to kind of, make it a little bit easier to see here. So their center of mass is going to be approximately right where our belly button is. We're assuming, kind of average body type, where all things are kind of equal. Basically a symmetrical body. But if they throw out their legs and arms, let's say to the right, because this person is facing us. I'm a very poor drawer, so we're just going to deal with that. But they are pushing their limbs or pulling their limbs towards the left here. their center of mass was here, it's going to go to the left. So their center of mass may be placed here, if here, here, or here, but their center of mass is going to be pulled towards the left, away from the center. So let's talk about weight. Weight is the amount of gravitational force exerted on a system. What we care about here is gravity. That's going to be the main component of our weight. Mass is important, but gravity is just as important. So weight is equal to mass times gravity. Generally, when we're looking at people on Earth, we're assuming it's 9.81 meters per second squared. This negative sign right here indicates that it's pulling downwards towards the center of the Earth. Generally, we don't, if we were to look at weight and we're calculating weight and we use negative 9.81, we'd come up with a negative value for weight. That doesn't quite work. If we're looking at just measuring weight, we'd say somebody is negative a certain amount of newtons. If we're looking at a free body diagram, we may use that. But generally, you've got to use a little bit of sense for what you're calculating, whether it should be negative or positive. But this is the acceleration due to gravity is negative 9.81 meters per second squared. And we use either a newton or a pound. Newton if we're using metric, pound if we're using imperial. Once again, this class we use metric unless it's otherwise specified. It always acts towards the center of Earth or a planet or a body. If you're out in space and there is a more massive object than you, you'd generally be pulled towards it. We see this we can even see it on Earth, but it's harder to determine because usually there's no object on Earth that is bigger than Earth, because that would be very, very odd. So generally we don't see it to that degree, but it always acts towards the center of the Earth. We're only going to be talking about biomechanics that are done on this planet for this class, so we'll stick with center of the Earth. Because gravity is different on different planets, mass is the same, but weight is different. Once again, if you're looking at weight loss, you can't really lose weight besides chopping bits off yourselves or moving to like the moon or Mercury or Venus, okay? And you wouldn't survive long on Mercury, Venus, or the moon anyway, so it doesn't really matter. Next, let's talk about pressure. Pressure is a force distributed over a given area, okay? So pressure is force divided by the area of an object. If we're looking at, generally, if we're looking at, a square or something like that, area is equal to length times width, but we won't need to know that. But our units are Newton meters squared, but we generally use pascals. Pascal was the name of a scientist that worked with pressure, and he developed all the rules of how pressure works. This is his equation right here. So once again, we name it pascals. If we're using heavier force, we may say kilopascals. If you're looking at the air in your tires, you may have seen the air in your tires are measured in pounds per square inch or PSI. But if we're looking at tires that come from a different country besides the US, Liberia, or Burma, you'll definitely see, especially in like the little door of your car, you're supposed to inflate your tires to a certain amount of kilopascals. It'll look something like this, okay? So we look at pressure is a force as well. It's distributed over a given area. And then we have moment of force. Once again, we have another name for it, is called torque. So we'll say moment of force is also equal to torque, okay? Usually you'll see something like this. This is a symbol for torque. But we're looking at, it's a linear force and are represented by vectors, okay? So when we're looking at the moment of force, we have our axis of rotation, axle of the wheel. Our moment arm, which is usually the radius of that wheel, this right here, is our moment arm. It's the perpendicular distance between the force, or where the force is applied, and the axis of rotation. So let's say we're loosening a bolt, okay? This bolt may have, and we apply, let's say, 10 newtons of force to this bolt, and we have a wrench, or the radius of this bolt is 0.006 meters. So convert that to centimeters in your head, and we'd have roughly 0.06 newton meters. So this is important right here. When we are measuring torque, or the moment of force, because we're multiplying force times the distance or length of our moment arm, we're using newton meters. Newton meters is generally going to be, if you're asked a question on an exam to calculate moment of force or torque, your units should be in newton meters, unless it's, once again, otherwise specified. Let's keep talking about our moment of force, and more importantly, the relevance of the moment arm. So a lot of times you'll hear lever arm. The distance or length of the moment arm provides a mechanical advantage. In other words, we're saying it's just as effective with a greater moment arm as it is with the force applied, okay? Especially if we're looking at metabolic cost. We'll talk about the patella in your knee or your kneecap in a little bit, but we'll look at how your patella moves that provides a mechanical advantage, especially when we're looking at leg extension, and it helps with diminishing the metabolic cost of leg extension. Well, let's say we're using a wrench to loosen a bolt, and we have different sizes of our wrench. So let's look at the first case, where we're seeing, once again, we have a radius of 0.06 meters. It requires 0.06 newton meters of force to loosen that bolt. But if we then say, well, we're going to use a longer wrench that is roughly 10 or 0.2 meters long, it only requires it requires a little bit more. It requires 2 newton meters of force. But it's easier to loosen that bolt with a longer wrench. So notice that the force is the same, but a large increase in the moment of force results when we're using the wrench. So we're using a mechanical advantage by increasing this lever arm here. It becomes easier for us to use to loosen a bolt, okay, to create torque. This is why oftentimes if you go to a car shop or a mechanic shop, you'll see they have different lengths of the same wrench, because sometimes a bolt needs a greater force to loosen, or if it's become rusted a bit, you need a very, very long wrench. You almost need a wrench you'll see some that are like the length of a person sometimes, but it adds a mechanical advantage to loosening that bolt. So we looked at a common example of a moment arm when we're looking at a longer wrench. It has a greater radius of rotation, or lever arm, or moment arm, whatever you want to call it. So we look at it having a mechanical advantage. But when we look at the human body, we look at joint moments of force. So muscles cross each joint, and the linear muscular force acts to alter the angular rotation of that joint. Okay? A linear force is creating an angular motion. Remember, when we see that we're looking at linear and angular force, so linear and angular force, we have general motion. Okay? So this is when we start looking at kind of human movement, is the muscles are producing a linear force, but because a limb rotates around a joint, it creates that linear force creates angular motion. So let's talk about the motion of force. This is our rotary force. Once again, this is often our F of y. Okay, it's usually determined using the sine of theta. We usually determine F of y. So this rotary force is the angular equivalent of linear force. A force is applied to an object causing it to rotate. So this right here is our moment of force. It is equal to the force created by the muscle times the moment lever, or our lever arm, okay? So if we're saying that moment M equals the moment of force, force, or F is the force, and dt, or our lever arm, is the perpendicular distance from the force's line of action to the axis of rotation. This is our moment arm, our lever arm, torque arm. You'll hear a lot of terms from it. We usually just say moment arm, okay? This is just as important as this. This may be more important in some cases where we look at certain types of joints and segments in the body as well, where the moment arm becomes very, very important, even more important than the force applied by the muscles. So let's, once again, we'll kind of look at pushing a door. Okay, so everybody's kind of opened a door by pushing it. So let's say we're opening this door and we're applying 10 newtons of force when we open this door, but we're opening it closer to the hinge of the door, so roughly 0.1 meters from the hinge. So right here and here is the hinge of the door. If we do that, we are only really pushing on the door with 1 Newton meter. Okay, but if we push further away from the hinge, closer to the handle, so we're pushing with still 10 newtons of force, but we're pushing roughly a meter away from the hinges, we are now pushing or rotating the door with 10 newton meters of rotational force or torque. Okay, it makes it easier for us to open that door. So what do you have to do to the force to push open the door in the first situation? You have to apply more force, more linear force. But by simply pushing the door that is further away from the hinge, we are increasing the moment arm, where we create a mechanical advantage. So we don't have to push as hard against the door because the moment arm is greater. Okay? This is why if you're opening up a door, you usually push where the handle is, because that's the furthest away from the hinge. What if you only need 10 newton meters to open the door? Okay, once again, when we look at this, is if we're pushing, close to the hinge, we have to use 100 newton meters of force to have 10 newton meters of torque to open up the door. But if we push further away from the hinge of the door, we need 10 newton meters of force, and we're pushing further away, so we can simply divide by 1 here, divide by 1.0 here, and this will cancel our meters, so we'll be left with newtons, and we only need 10 newtons of force to open up the door. Okay, so therefore, by simply increasing the moment arm, we also reduce the effort or our force our bodies need to produce to achieve the same result. In this case, opening a door. So how can we calculate our moment arms? Okay, the moment of force has 2 determinants. One, the force, the applied force, and the moment arm. The moment arm, once again, is the perpendicular distance from the line of action of the force, this is our F, to the axis of rotation. Sometimes we'll say A. You'll also see, once again, this symbol as well. Okay, it's usually say it's the moment arm, line of action of the or axis of rotation, Sometimes you have a torque arm, but usually we say moment arm. You can consider the axis of rotation in the following examples. We're going to look at as a pin attached to the table, and the system rotates around the pin. Typically, when we're talking about moment arms, we're using meters or centimeters, but we like to convert to meters before calculating the moment of force. Okay? Makes it a little bit easier to determine it. So, steps to find our moment arm. First, we extend the line of action of the force with a dashed line. Then we draw a perpendicular line from the line of force to the axis of rotation. Then we use good old trig. However, it's very, very important when you want to find the length of the moment arm, you cannot solve for length using units of force. You have to use meters. Therefore, when solving for the moment arm, be sure to use the side where you know the direction. Okay? This is very important. It's hard to extrapolate the length of the moment arm. Usually you'll be given the length of the moment arm, but when you're solving for it, be sure to use the side where you know the distance. Okay? Try not to use guesses. So, if the system was not pinned to the table, let's say you put a piece of paper on a desk, okay, and you're just pushing on it, it's going to cause translation, that translational force. Once again, that's kind of our f of x force. And it's simply going to move straight like this, okay? It's going to keep moving nice and straight. But because, let's say we put a pin, or we just put, I don't know, like a heavy coin on this piece of paper right here, and we're still pushing like this, it's going to start rotating around this axis, okay? It's going to rotate around point A, the axis of rotation. So it's going to start rotating around this point, so that's where we see this counterclockwise motion. Once again, this would be positive because counterclockwise is positive, clockwise is negative. So let's say we want to measure the rotary force or the moment of force. First, we extend the line of the force, just like that. Then we draw a perpendicular line from the line of the force through the axis of rotation, the line at our bottom edge here. Okay. Then slide the paper along until the other edge passes through the axis of rotation. Just like that. The moment arm is the line along the edge of the paper. Okay. So this is our moment arm right here. Okay. So this is going to be, this part right here is going to rotate. I'll use a different color, a little bit wider, is going to rotate around our axis right here. So once again, we have this. So we simply draw a line, use a different color here. That it's not perfect. I'd use a ruler, but I don't really have one on my computer screen. This is our moment arm. Okay. So it's going to, depending on how this force is applied, it's being pushed down and to the right, it's going to start rotating like this. It's going to rotate in a clockwise motion. If we're looking at this one right here, and sorry, they're not straight lines, okay? Oops, I don't know why they got deleted there. This is our moment arm right here, and it's going down and to the right. Okay, so it's going to start rotating like this. Okay, so that's where we start looking at our rotation. The moment of force is one of the most important concepts in biomechanics because it measures the ability of muscles to cause rotation. Once again, this is, if you want a good symbol for it, this is our F of y. And we usually use sine to calculate F of y. Usually F of y is sine of theta times our force. It's usually a resultant force. Okay, so we can look at the biceps as they insert on into the forearm, and we can look at the kneecap or patella of the knee. So right here, once again, we have our biceps are inserting from our humerus to our ulna and radius here, and they are, we'll say, are doing concentric contractions, so they are shortening towards their center, and they're going to be pulling up. I'm going to use a different color. And be pulling up on the forearm here. When we have our bones, here, we've already kind of created a triangle right here. This is our right triangle right here, and we know this angle here, we know this angle here. If we know the force of the biceps right here, we'll say F of B, we simply create another triangle like this, and we know F of B. We know this angle, we know this angle, we know this is a right angle. We need to solve for F of y. This would be F of x. And we know F of y of the biceps is equal to the sine of theta. This is theta right here, times F of b. If we wanted to calculate F of x is simply b equals the cosine of theta times F of b. Okay, so the insertion of the biceps on the forearm is very important. Does it insert close to the joint or away from it? If it's inserting further away, it's going to create more moment of force, okay, a greater amount of torque. If it's connected closer to the joint, it would produce less. So let's take another look at this. What mechanical advantage is gained by the insertion demonstrated on the left versus our right? So when we're in pronation, we have a greater moment arm than when we're in supination. So we can create more rotational force with our biceps because our biceps are always going, we can't really change the amount of force our biceps can create. I mean, we can with weight training and everything like that, but it's easier for us to create more rotational force with a longer lever arm than it is simply by more force of the biceps. So here we can create more rotation. So this is similar to the patella or kneecap, okay? When we go into extension, our patella goes up, it rises up into the intercondyle groove of our femur, and it creates a greater moment arm for our quadriceps. And we'll see a demonstration of that in just a bit. What that does is it increases the amount of torque our quadriceps can produce. In fact, it doubles the amount of force the quadriceps can produce. It's actually quite nifty. If we're looking at, they don't do it much anymore, but sometimes we're looking at knee injuries, or sometimes there was cancer of the bone, or you got terribly injured. Sometimes patellaectomies, they would cut out the patella of the knee, and that's where we'd see basically the force of lengthening your leg would be cut in half, essentially. So the patella is actually quite important. So when we look at what the patella does, it's increasing that axis of rotation, or our moment arm or lever arm. Therefore, the patella provides our mechanical advantage. So let's take a quick look at this in this next little video here. So we'll say that this rubber band here, okay, is our quadricep group. So Q for quadriceps. This right here is our lower leg. This right here is our femur. And then this little pebble right here is our patella. Okay, so when we have our patella, this is kind of the quadricep tendon right here. It makes it, we see that this person doesn't have to pull on this rubber band much to cause any sort of rotation. Okay, her hand is moving a little bit less. But when we take the patella out, look how much we have to pull on this rubber band to do very minimal movement of the leg. So what the patella is doing is it's increasing the moment arm of the quadriceps. So it's creating that mechanical advantage, and we're looking at much, much more efficient leg extension through our quadriceps. So we haven't really talked about the other side of moment yet. But can we say that we have positive moments and negative moments? Yes. Okay. So a negative moment and a positive moment. When we're looking at moments, we're looking at the tendency of force to produce rotation in the same, is the same. The amount of force is the same, but the direction is different. So remember when we were looking at angular kinematics, we said that counterclockwise rotation is positive and clockwise rotation is negative. Same thing here, okay? But the absolute value of moment indicates the magnitude of the moment, and either it's plus or minus indicates the direction of the moment. So it's either positive in counterclockwise or negative in clockwise rotation. So let's talk a little bit about our external versus internal forces and moments. Forces are applied to a biological system, and these can be considered either to be external or internal forces. Our external forces include gravity, is our big external force that we consider for this class is gravity. But we can also look at our wind resistance, buoyancy, the normal, the reaction force, the ground reaction force, if we're holding extra weight on ourselves, stuff like that. So it's another person. Our internal forces include our muscular forces, okay? We can look at pressure too. If we really wanted to be fancy, we can look at pressure, especially blood pressure within the heart. We can look at the biomechanics of the heart as well. But for this class, our internal forces are our muscular forces. We're going to wrap up this lecture. We're going to talk a bit about impulse, especially linear impulse. Linear impulse, we're looking at the area under the force-time curve, okay? So this is our force-time curve. Force is on our y-axis, time is on our x-axis. This area in here, color it in as much as I can, is our impulse, okay? If a force of the same magnitude is applied for different durations, different motions result, okay? So in situation A, motion in B will be greater than in situation A because we're applying approximately the same force, but we're applying it for longer. So once again, let's look at situations A and B. A and B have a similar impulse this time because while the force in situation A, once again on the y-axis and time on the x-axis, here the force is greater, but it's applied for a shorter amount of time compared to situation B, where the force is less, but it's applied for a greater amount of time. So we see a similar impulse. So we're looking at force over time. So our linear impulse is simply force times time, okay? This nifty symbol is our integral. If you haven't seen this for a while, we can start getting into calculus, which is oh so much fun. But basically we're looking at force over time, okay? Linear impulse is the area under our force time curve. So what is momentum? Everybody kind of says, examples of cars having momentum, boats, games, teams, whatever. Even politicians, they have great momentum, they have little momentum. But momentum is simply described as the amount of motion an object possesses. It is measured by a product of a body's mass and its velocity. So this is momentum right here. So we have mass times velocity. Mass is often used in kilograms, velocity in meters per second. So a lot of times you'll see units of momentum are kilograms per meter times meters per second. Okay, it's a terrible S like that, or you'll see it like this. Okay, those are the units for our momentum. And we'll talk about momentum in greater detail when we start talking about linear kinetics. But generally, momentum is the quantity of motion that an object possesses. How much momentum does a stationary object have? Well, when we look at this, it could have all the mass in the world, but if velocity is 0, momentum will equal 0. Whenever you multiply anything times 0, it has a product of 0. Okay? So momentum is a component of the biomechanics principle summation of continuity of segment velocities. So a lot of times if we're trying to determine momentum, we may do a free body segment on free body diagram where we're measuring the momentum or velocities of each of the segments to determine the entire body's momentum. But we'll look at this in greater detail in the next lecture when we talk about linear kinetics. So once again, I hope this has been helpful for you guys. Once again, please watch this. If you have any questions whatsoever, feel free to contact me. I prefer you contact me before the exam that you will be tested on. This will be in exam 3, just to make sure that you guys are prepped for exam 3. We'll be doing a small lecture to review for exam 3 as well, but this will kind of be a big part of the exam. So if this kind of stuff is you're still a little worried about it or anything like that, feel free to contact me. We can talk about it during office hours. We can do a private Zoom meeting. We can do it over email. So if you're still confused, please contact me. Have a nice day. Goodbye.